gravitation, as I call it, the undiscovered obvious force. Everybody feel it, everybody experience all the effects of gravitation in all natural world applications. However, not a single scientist defined the gravitation exactly with a single equation. So that is a kind of inspiration for you to dig more into gravitation and use the science that you will learn in this course and in the future to be able to solve this mystery of gravitation. There's many scientists like Newton and Einstein who are getting near. Some of their theories are being accepted by the scientific community. Some of them are being reverted. Some of them are being questioned. Everybody is having his own belief and his own imagination about gravitation, backed by many mathematical equations to be able to tell that what he thinks is the truth of gravitation. Gravitation is considered one of the weak forces in the universe. As you know, we have main types of forces. We have the nuclear forces and the gravitation. Nuclear forces here means the forces between the atoms. That's considered a weak force. Gravitational force, surprisingly, is considered a weak force. However, making anybody laugh when you know that this so-called weak force is holding the universe all together. We will learn in this section of the course about gravitation. We studied a little bit about the gravitational acceleration and gravitational force. In this little section, we will talk more in details about the gravitation on the scale of the universe. So, gravitational force, as you may already know, when we are talking about gravitational force on Earth, that is the gravitational force affecting objects on Earth. As we discussed before, you have your mass. The mass is being influenced by the gravitational force coming from Earth. Your mass is pulling you downwards towards Earth, and Earth is pushing you in a normal force backwards. So always when you talk about gravitational force exists in pairs, which means as the mass of the object is being pulled downwards towards Earth, there is a normal force pushing that object upwards. And we discussed that through the Newton's third law, if you remember. And if the Earth is exerting gravitational force of magnitude 700 newtons on you, then you exert a gravitational force of magnitude 700 newtons on Earth. It's kind of, you are in a daily unnoticed fight with Earth. It's pushing you upwards and telling you get away, and you are just pushing her with the same exact force downwards. You are beating each other all year long. Earth attracts you and you attract Earth. It's a love-hate relation in this case. The force you exert on Earth has a negligible effect because the Earth mass is known by scientists for the best number of 5.97 multiplied by 10 to the power of 24 kilograms, which is a huge comparison to your weight. But you need to keep in mind that the gravitational force that the Earth exerts on you causes a notable acceleration because of your relatively small mass. So, the imagination or the explanation of Earth gravity or gravitation up to this day within the Earth atmosphere is basically many objects or all objects on Earth are smaller than the Earth in mass. We will learn a little bit about how Newton succeeded to come up with some expression about how things are pulling each other in the universe. But for now, I can tell you that your mass is too small to pull the Earth, but the Earth is too big that you can overcome that pulling force on your body. So when you throw a ball upwards, it will come downwards. When you throw yourself off the building, for sure you will land on Earth. And because you're being pulled in a way stronger force of pulling, which is the gravitational force that's pulling you always downwards to its surface. So Earth is our loyal mom. It doesn't like anybody to leave it. It's just pulling all the objects on it downwards to its surface. You may be asking, okay, how about rockets? Well, rockets are exerting a big force to be able to reach what is called as the escape velocity or the escape force. That is the force you put in stronger compared to your mass versus the mass of Earth. That force is stronger than the force pulling you downwards to come back to the surface. If you fail to generate enough force, the rocket will come back to Earth and explode. But if he succeeded to generate more force to escape the atmosphere, then in this case the object is free and he will be swimming in the universe. The concept of weight, we said there is a strong independent and direct relation between the mass and the gravitational force, for the fact that scientists found gravitational force equals the mass multiplied by the gravitational acceleration. So your body is always attached within the gravitational force to stay stable on Earth. It's a good thing, obviously, to be able to do the daily application and drive your vehicle to work and be able to put your cup of coffee on the table without floating around, as you already know. The more you weight, the more the Earth is pulling you with a gravitational force. This is why, in the ideal world, without vacuum, with air resistance, if you drop a heavier object, it will slam the surface of the Earth stronger than the lighter object. That's why when you throw an ant over a building with 20 stories, most likely she will be fine. But if you drop yourself from a 20 stories building, you will be in pieces. But in the ideal world, if you remove all the air from the atmosphere and you jump you and ant from a 20 stories building, theoretically you will reach both at the same exact time because you are being pulled through the gravitational acceleration and gravitational force. We discussed that and we solved many problems on it, but just to remind you and to connect the dots together with the subject we're talking about here, if you have a bag of apples and you hang it on a Newton's scale, which is a scale with a gauge that will tell you what is the gravitational force applied on the scale, which will tell you what is the gravitational force applied on the bag of apples. So you have gravitational force pulling downwards, you have the spring force pulling upwards, and the gauge will stop at a certain point. That is the gravitational force being applied on the bag of apples. So the F net in this case, if you analyze the vectors, equals the gravitational force. We know that F net can be represented as mass by acceleration would equal gravitational force. So, which means gravitational force equals mass multiplied by gravitational acceleration. So the gravitational force acting on an object is the same whether or not the object is at rest or moving. So the equation relates the gravitational force acting on an object, and that would be called the weight of the object, or it is mass. Now with Einstein coming out with the relativity concept, there is more louder sounds coming up saying that, okay, what is the difference between the inertial mass and the gravitational mass in this case? Einstein eventually told the world that gravitational mass is exactly the same as the inertial mass. They're all being standard in the universe. You have a mass and you have gravitation, and that will generate a gravitational force applied on that object. So the mass in this equation of Fg equal mg determined by finding the ratio of the gravitational force acting on the object to the acceleration due to gravity. So since the Fg and the g are in the same direction, the scalar form of the equation can be used as Fg equals mg, which means the gravitational mass would equal the gravitational force over the gravitational acceleration. That's what we call gravitational mass. It means you found the mass through analyzing the gravitational force and the gravitational acceleration. Divide gravitational force over gravitational acceleration, you will get the mass of that object. Now something to mention with gravitational force. Gravitational force generates gravitational field. Imagine it as a magnet As you know, the magnets have a south and a north pole. When you have two magnets near to each other at certain distance, you'll feel there is an effect, there is a force going on, either pulling or pushing each magnet away from the other. And that is what we call in the electrical science the field, in that case, either magnetic field for the magnets or gravitational field for the gravity of Earth. So the Earth is generating a gravitational field. Scientifically, it doesn't look exactly like this, but for simplicity, you can imagine it as arrows pulling downwards to the center of Earth. So the Earth is kind of different kind of magnet, but it does the pulling force on nearby objects. That includes us, includes anything on the surface, and includes planets who are in the range of that field. So the moon happens to be close enough to Earth by theory of having always a steady pulling force between the Earth and the moon. The moon have a smaller mass than the Earth, and the moon keep rotating in a path, circular path around the Earth. He never fall down, he never escape away. That's how things happened after a long time after the Big Bang, and when the planets are formed. The moon happened to be in exact distance to keep rolling around Earth in almost steady distance from the center of Earth. So physicists define field as a three-dimensional region where there is some type of influence, whether it is attraction or repulsion on the nearby objects. Since every object exerts gravitational force in 3 dimensions, it influences the space around it. This region of influence called gravitational field, and it is through this region that the two objects interact, as we see in the example of moon and Earth.